Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. And today we are going to go over Stokes' theorem, which is an extension of Green's theorem, but on higher dimensions. So what that says is if you are taking the integral along a curve f dot dr, this can be represented by the double integral over surface of the curl of f dot dr, ds, not dr. Okay. So you are simplifying one integral, like a one-dimensional integral, into a double integral? Yeah, because sometimes it simplifies it. If you have multiple surfaces, then performing the line integral would be like several integrals that you add to each other, but that is simplified by Stokes' theorem, as we will see. So the idea is that we will have a surface that we will need to parameterize. We are going to get the curl of f, which is easy, and then perform a dot product. Because when I say dot ds, remember what we did. We took two directions, u and v, or even x and y, it doesn't matter. When you do the cross product, the cross product gives you the area of the parallelogram of RU, R sub x and R sub y, or R sub u and R sub v, times the unit vector perpendicular to the surface. And like we saw last time, if you take the curl and just make a dot with the normal, it gives you that in the direction perpendicular to the surface. So where are the examples? Here's one example. Well, in fact, I can rewrite it because it's bad. I don't see, did I? Let me make another copy. No. So it says the following. Let me write it because it's very handwriting is bad. Don't think you'll be able to read it. I want to evaluate this integral where f of x, y, and z is basically given to me as negative y square I plus xj plus z square k. And the surface, because notice we are going to do a double integral over a surface, and this surface is intersection of y plus z equals 2 and x square plus y square equals 1. So basically, if you draw this surface in the xy plane, meaning at z equals 0, you will get, let's draw it like it's a circle, but I have to draw it with the inclined thing. That's the center is the origin, the radius is 1. And then I have here an inclined surface cutting it, and that surface is y plus z equals 2. This surface cuts the cylinder at an angle, so it produces here an ellipse. And basically that's it. Okay, so when we start calculating the curl of f, that's basically a cross product of the del operator and f. The del operator is partial x, partial y, partial z of negative y square x z square. So what does that give? In the I direction, I get partial y of z square is 0 minus partial z of x is also 0. So I get 0i. When I go to the j, notice we do it backwards. Partial z of negative y square is 0 minus And then partial x of z squared is also 0. So I don't have i's or j's. In the k direction, I get partial x of x is 1 plus or minus partial y of negative y squared would make that positive, and the derivative of y squared is 2y k. So that's the curl of f. Now, what is my position vector r? Hmm. So notice we are only going to parameterize. The parameters are x and y. So I would have xi plus yj. And then instead of z, I'm going to say plus 2 minus yk, right? And finally, when I get dr, meaning if I take the derivative of r with derivative of x with respect to x is 1, so I get I. Derivative of uh, x or y with respect to x, so this is in the x direction, I get 0. And the derivative of 2 minus y with respect to x is also 0. Then ry, the derivative with respect to y, it's 0i plus j minus k. Notice in order to find a normal, the normal, which is n, I would have to do rx cross ry. So another cross product, ijk 1 0 0 0 1 negative 1. So it equals. First of all, let me rewrite f. F is 0i plus 0j plus 1 plus 2yk. Now, when I do this, I will get rx cross ry equals. In the I direction, I get 0 minus 0, so 0i. In the j direction, I get 0 minus negative 1, so plus j. In the k direction, I get 1. So now when I perform a dot product between these two guys, 0 and 0 will give me 0. 0 times 1 is 0. And 1 plus 2y times 1 is 1 plus 2y. So that's basically it. Now I need to integrate. But in order to get the integral, it's much better to use polar coordinates. Okay? Why? Because now y would becomes r sine of theta. So now I'm going to take a double integral. R goes from 0 to 1. Theta goes from 0 to 2 pi. And my integral here is 1 plus 2r sine theta. And then my dx dy become r dr d theta. So I'm going to take the integral from 0 to 2 pi of n times or integral of that r plus 2r squared sine theta dr d theta. So we are going to perform the integral with respect to r, which will give me r squared over 2 plus 2/3 r cubed sine theta. This whole thing is evaluated from 0 to 1 d theta. Now, if r is 1, you get integral from 0 to 2 pi of 1/2 plus 2/3 sine pi, sine theta, d theta, right? If you substitute r is 1, so r squared is 1, r cubed is 1, everything is 1. So when I integrate that, I will get theta over 2 plus 2/3, no, minus 2/3 cos theta evaluated from 0 to 2 pi. So I get, in the first pair of parentheses, I substitute 2 pi for theta, so 2 pi over 2 is pi, minus 2/3 cosine 2 pi is 1, so minus 2/3. And then you substitute with 0. 0 over 2 is 0, minus, and cosine 0 is 1, so minus 2/3. So I get negative 2/3 minus negative 2/3, cancel, and my answer is pi. So that integral would yield pi. Okay, so that's the first example. Maybe I made it, I should have reduced the size. I'm zooming too much so you cannot see the original problem. I think I need, let me try to, sorry guys, I just want to reduce the zoom a little bit. I think that would allow you to see better. Maybe I needed to decrease it more. I'm sorry. Okay, so that's the first example. I think you can see it. The second example here tells you to evaluate that integral, and they give you the the field is x of xyz is yi plus zj minus xyk. And S here, we are in the first octant, meaning x, y, and z are positive, right? Did I write it correctly? 4 minus, yeah. They tell you it's in the first octant, and the z equals 4 minus x minus y. So, same idea. We are going to find first the curl of f, which is the del cross f. So I get I, j, k, partial x, partial y, partial z of y, z, negative xy. So in the I direction, I get partial y of negative xy, which is negative x, minus partial z of y, which is 0. Then in the j, I start, wait a second, I'm sorry, guys. In the I say partial y of negative xy, which is negative x, minus partial z of z, which is 1. So minus 1, not minus 0. When you go to the j, you do partial z of y, which is 0, minus partial x of negative xy, which is negative y, but I have negative, so that becomes yj. And then in the k direction, I get partial x of z minus partial y of y. So really I get negative x minus 1i plus yj minus k. I think we did that correct. Okay. Now, we are in the first octant from the xy plane to the plane z equals 4 minus x minus y. So the next step, we are going to write r as xi plus yj minus, plus 4 minus x minus yk. So partial r in the x gives me I plus 0j minus k. And ry becomes 0i plus j minus k again. So Rx cross Ry would be ijk 1, 0, negative 1, 0, 1, negative 1. So Rx cross Ry equals, in the I direction, I get 0 minus negative 1, I get 1. I. In the J direction, I get 0 minus negative 1, so J. In the K direction, I get 1 minus 0, so plus K. I plus J plus K. Now, when you do the curl of F, dot that, so I'm going to multiply negative x minus 1 times 1. So I get, the curl of F dot n ds, which is Rx cross Ry. This whole thing would give me x, no, I'm sorry, negative x minus 1 plus y minus 1, right? I think that's what we get. Negative x minus 1 times 1 is negative x minus 1. Y times 1 is y, and negative 1 times positive 1 is negative 1. So that is basically negative x plus y minus 2. So now you have to take the integral. Notice at the bottom, when z is 0, I will get the double integral of x and y. X goes from 0 to 4 minus x, right? And then the y goes from 0 to 4 minus x, and the x goes from 0 to 4. I started with dy first, since I took those limits with respect to y. So I get 0 to 4 of negative xy plus y squared over 2 minus 2y evaluated from 0 to 4 minus x dx. I don't care about the 0 because that would give me 0. So what I will get is integral from 0 to 4 of negative x times 4 minus x plus 4 minus x squared over 2 minus 2 times 4 minus x dx. So let's simplify. Well, I have negative and negative. I think you can just say, okay, so it's the integral from 0 to 4 of x squared minus 4x. And you know that 4 minus x is the same as x minus 4 when you square it, right? You should know that. So that becomes plus x squared over 2 minus 8x over 2, meaning minus 4x. And then even when you say x minus 4, the 4 squared is 16 over 2 is 8. Okay, I hope I'm doing it correct. Let's make sure we didn't mess up. X times 4 minus x, so negative 4x plus x squared. This is x squared minus 8x plus 16 over 2 minus 8 plus 2x. Yeah, so the 8 and the 8 cancel. We still can simplify more. So from 0 to 4, I get x squared, 3x squared over 2. Negative 4x minus 4x is negative 8x plus 2x is negative 6x. Hopefully that would be correct. I didn't mess up anything. So it equals the integral or antiderivative of x squared is x cubed over 3. So the 3 and the 3 cancel. Just to save you time, it's x cubed over 2, right? It's x cubed over 3, but it's multiplied by 3. They cancel each other. Minus x squared over 2 times 6 is negative 3x squared, and this is evaluated from 0 to 4. So in the first pair of parentheses, I get 4. Notice the 0 is not important. Why did I open parentheses? It doesn't matter. Here it doesn't matter. So 4 cubed is 64, over 2 is 32, minus 4 squared is 16, times 3 is 48. And 32 minus 48 is negative 16. And hopefully this is the correct answer. I think we check that. Yeah. So that's it for Stokes theorem. These two examples try to illustrate how it works. And again, as usual, if you have any questions, don't hesitate to drop me a comment in the comment section, and I will try to get back to you as soon as I can. Otherwise, I wish you all the best, and until we meet again. Bye.